you guys could chat with some ideas of some words you would like to discover the ness of, and I will bring up some scripts that you can use in this package called nessvec. You can pip install nessvec. It may or may not install correctly and with all the dependencies you need, but I've got it all working here on my computer, so I will show you how to use it. It's in chapter 6 of the natural language processing in action, and we're talking about nessvectors and the nessvec package. What it does, it allows you to analyze the components of a word so you can tell how much hotness there is in a word like red. Let's see if we can import nessvec. Great, we don't need to do it that way. We can, let's see this for, I'm going to activate a different virtual environment. Because I know it worked over here. Now let's see if there was any run commands. Oh darn. There it is. I just need to get in the right directory and this will all work. So Maria and I are from Tangible AI. She's on chat. She's also the co-author of the book. Let's see. We're now in CD into nessvec. So I've installed it from source, so I don't need to have all those imports working. So I can CD into the source directory within there. So you want to git clone nessvec from GitLab if you want to follow along or reproduce these results later. So now I'm going to CD into the actual nessvector Python code with some examples. We got Maria voting for nessvectors because she knows that's the only thing I've tested and she doesn't like it to see me flounder. If anybody else joins us, feel free to chat and give me your ideas for words you would like to discover the ness of, or even names. Since the title of this talk is about what's in a name, we can do this on names. We did it at our mob programming session Wednesday night with some really odd names like Kamal and some of the other teammates that we have from around the world. Let's see if we can reproduce those results. So let's do that run indexers. So indexers contains a script that will load a bunch of fast text word vectors. I'll open up another terminal so we can wait. It takes about 5 minutes to index these word vectors. It might take longer since I've got this streaming session running. Let me make this bigger. And actually, let's exit. Work on nessvec to get in the right directory. And then conda activate the right environment. And then we can make this text bigger so you guys can read what I'm talking about. Fortunately, I can't share a picture-in-picture of my face. I know that's not fun. Let's see what we got on chat. Allan, we got a word for Allan. It is someone named Allan, perhaps Allan Axon. AJ Axon. So we'll look for the names AJ as well as Axon and Allan. And we'll see how similar they are in meaning to other words that you might be interested in, like maybe coolness or hotness or other words. So how much of your name contains those sorts of things. So the indexers are still running. Let's, so I need to CD into SRC, CD into nessvec. I can do some other things while we're waiting. Perhaps I can show you the code that's actually running right now. That's probably a good idea. So let's look for that index. So I'm using Sublime, awesomest text editor in the world, completely free, and not open source though, unfortunately, because he has to make a living, the developer of this. He's started to build up his team because it's gotten pretty popular. Out of Australia, I think. Let's look for the indexers file so you can see what's running in the background over there. There's a million of these fast text vectors, so I can explain why this is taking so long. and why you even need an index. So you can search for two-dimensional positions. Like if you're looking for the nearest location of, say, a coffee shop, you can search for that in 2 dimensions quite easily just by creating a box around you and expanding that box. But you only have 2 thresholds, you know, the min and the max on each of those 2 dimensions in order to search, and gradually work your way down through a binary search tree to find all the things that are within that query you're doing on a database. Can't do that with continuous vectors and high dimensions because it would take forever, infinitely long. For one thing, those boxes contain, either they contain nothing, so those 300 dimensional boxes that you typically have for a word vector would contain nothing, or they would contain everything, because everything is kind of located on the unit sphere. So you can imagine a box expanding inside of a unit sphere, and as it got out to that edge, at that 300 dimensional sphere's edge, where all the points are, all the vectors are, it would grab the 6 corners, or in this case, the 300 times 6, I don't even know what it is, 300 squared maybe, corners of that hypercube would touch that sphere. And so you would, as you're expanding it slowly, really small increments, you would still capture a large number of points when you suddenly hit the sphere, and none of those points would be close to each other. And so there's no easy way to use box and sort of KD tree search of high dimensional space of continuous vectors. So that's why we create these indexers. Let's find that indexers file. It's in source under nessvec indexers. There they are. So it created a simple wrapper for the pin descent indexer. Let's see, actually I can probably run some of these other functions. So I'll do an import star of that. Let's see if it's how it's going. Still running. From indexers, import star. So the pin descent, PYNN, Python neural network gradient descent algorithm for creating a machine learning index, a learnable index of where all the vectors are. I think there's some, let's see what's in our namespace. I think there is a load, so we can load the analogies. We should probably look at that first. Well, let's load some vectors first. I thought there was a load vectors function in here. It doesn't look like there is. Index vectors within the, let's see, a load HDF5, that's what it is, because I'm not actually loading it into RAM, so it happens instantaneously. It doesn't actually, the million fast text vectors, million times 300, takes up a lot of RAM. So I'm going to call that vex, because that's what I think it's doing in the other terminal. It's loading them the same way. Great. So we ran into this error that our analogies contain words that we don't contain, that aren't in the fast text index. So unfetter, pinioned, recite, and practiced. Whoa. Oh, it doesn't know which of these words. So at least one of these words. So it looks like it's the unfetter word that's missing, and pinioned, because those are the only ones that are common to all these queries that it did on these analogy problems. So the way word vectors are typically used is in analogy problems. It's the way that people can kind of understand them. Looks like there's some other words that are not understood. Probably this unfrock word. That's a pretty uncommon word. Looks like it's common to the next 3 of these. So that's an minister's here. So unfrock is here. So minister is common to them all as well. But I'm guessing it's unfrock. That's the word that's missing from the fast text library of a million word vectors. But let's see if once that loads, let's see if vex. Now I need to get the vex is actually a tuple. Now that I think about it, it's going to return both the words themselves as well as a data frame. So let's see what let's get that separated. So vex, comma, words, or vocab, we could call it in natural language processing. Vocabulary is a typical, and we're going to set that equal to this tuple that I accidentally loaded into the variable vex. Now let's see what we've got in vocab. So now we got the words and the vocab. So that gives us a mapping from the word to its row number in that million set of examples of word vectors from fast text. And now we've got the vecs themselves, where I can then use those words to find a word like Allan. So I'm just going to assume that Allan's in there. I think they've lowercased everything in fast text. So unlike Google Word to Vec, Google Word to Vec has some capitalized words and some n-gram words in there. I think fast text does not. They only contain 1 grams and they only contain lowercase words. There's another index that has a large number of partial words that can be combined together to create multiple words, like what's called morphemes, the portions of a word that actually mean something. So the smallest portion of a word, and those might contain 2 grams, or at least a way to construct 2 grams. So we've got a vector for you, Allan. Let's figure out now what it's close to. So see how close it is to, let's see how we're doing over on the indexer. Oh, not quite done. So let's see how close it is to your other axon name. So I'm going to do a dot product manually. Actually, I think I probably have some utils from util. Let me make sure tab completion is working great from util, so I don't have to know whether it has an S or not. Import star. Great. Now let's see what we've got here. I think I've got some cosine distance, cosine similarities. Great. Let's see if cosine similarities will tell us about the similarities to some other words. I wonder if I need to give it as 2 lists. Let's try it without that. Let's try it with just 2 words. Let's try hotness. Oh, it needs vectors. So we need to go back to our vecs and grab the vocab to get the index. That's what that index wrapper is doing that you saw in the code. It's actually, no, it's not. It's doing something different. It's it's reshaping an array into a list of vectors so that it will process in parallel quickly anyway, I'll stop talking about that. But anyway, I'm going to create a function in that indexer that will allow me to just look up a word so that these functions will be able to, you can give them either a word or a vector. Now let's see what happens. Field names only allowed for compound types. Ooh. Okay, let's see what cosine similarity signature is. Oh, we got cosine similarity. Maybe that'll work better. Let's look at that one. Just gives you 2 vectors. That's exactly what we want to use. So not similarities, similarity. Not sure what that other one does. Field names only allowed. What's going on there? Okay, let's just do the cosine similarity. I'm doing something wrong somewhere. Let's see if it's any of these. Make sure I'm grabbing the vectors correctly. Oh, I'm doing vex. Problem. Vocab. So that's what you're here for. You could probably chat to me. If we had audio, I'd be able to hear you, and you could chime up when I make a typo like that. But that works a lot better on our Wednesday night. If you want to join us for Wednesday night mob programming, where we do this kind of stuff, we do it on Zoom at UCSD. I'll put something on the chat channel soon, so you know the Zoom and the time and the place for that Wednesday night chat session, 5:30 Pacific time in the US. Vex, vocab. This should work better. This is another good debugging trick. Cosine similarity, parentheses around the vocab. Vex, square bracket vocab. Wonderful. Now this should work. Whenever you're debugging something, go into the individual expressions, make sure they all work. That's how I noticed pretty quickly before I even had to test it that was not working. So you're not very close to hotness, Allan. I'm sad to say. That's because that's not a name. Hotness is not a name. So a word vector contains a lot of qualities besides just one. So it is close to at least it knows it's a name. What about first name? We'd have to do, well, Let's see, what about first? Let's see if that is very close to you, but even further away from that. So that word has less. What about, we can add two words together to create something like first name. Let's try to do that just so we can, you see how that's done, even though it's not really going to be much better probably than the distance from the word name. But you can just add two vectors together. And what have we got? It's less close to that combination of two words. Let's do the, I bet the word index is done by now. Oh yeah, we ran into this bug before, but I think we've got an index that's working here. Let's see what we've got. Index, or I mean, is it called index? I think it is. Unfortunately, yeah, unfortunately, I did the bad thing in Python. Don't ever override what's a built-in function. Fortunately, there's no global function called index, but there is an attribute of any list called index. So you don't normally want to use that, and it's kind of a generic name. So I should probably call that word index or something, or just WV. Anyway, I've got in the index, and I can look it up by any word I want to find all the words that are closest to us. So instead of searching around randomly like I just was for that word vector Allan, let's make sure I've got the vex here, over here in this one. Okay, great. So that loaded correctly. And let's see if the vocab loaded correctly. Yes, it did. So now I can do that stuff with the index. Let's see if I can find some previous uses of that. Index dot query is the right way to do it. So this is a way, so I'm doing some word vector math. It's a lot of complicated stuff in this expression. So let's see, maybe I should do it on just, I'll simplify this expression so we can do it on just one vector. Allan. So this was checking the hotness, and it was trying to subtract hotness from the word red and adding coolness to the word red. I should actually check your similarity to the word hot rather than the word hotness. That should be a little closer than hotness. Anyway, that's what I mean when I say ness of a word. It's it's taking a word like an adjective like hot and then putting the ness, how much hot there is in the word Allan. That's the hotness of the word Allan. Let's see, what do we got here? I think this is the way the query works. So the query returns a bunch of things. It returns a list of it returns a list of two lists. Each of those lists contain index and contain similarities as well as word indexes, I should say. And so we have to do a lot of de-indexing to find the thing we're looking for. What we're looking for is the actual words that are close, the list of words that are of indexes that are close to the word for Allan. And then we send those into iloc because vocab is a data frame. So we can look at all the words that are close to Allan. Allan's closest to Allan, obviously. Edwin is very close to Allan. So is McKay and Hobbs. Wow, that's my nickname. So somehow we're close in an alternate universe where fast text is the only way that people understand words. Pretty cool. Let's see. Hobbs as a last name, though, with double B-S, the philosopher, without an E. That's interesting. Macintosh, you're close to the Apple PCs as well, I guess, the old ones at least.